Hey everyone, Mike here from ArnoldTutoring.com with a good calculus question. This is going to test our first and second derivatives and kind of some pieces how it relates to functions. So we've got our function. The first thing we're asked for is where is f increasing or decreasing? The words increasing or decreasing should be triggers to go after the first derivative. So what is the first derivative? It is, for exponential functions, we just rewrite the function times the derivative of what's inside, which is 2. Same thing for the second part, times the derivative of what's inside the exponent, which is negative 1. If we clean this up, it's 2e to the 2x minus e to the negative x. Now what do? We set this equal to 0 because increasing functions means a positive derivative, decreasing functions means a negative derivative. So we want to find the spots where the derivative equals 0 and then test either side. So I'm going to set the derivative to 0, and we have 2e to the 2x minus e to the negative x. It's not very intuitive how it is. Whenever we have something equal to 0, we'd ideally like to factor. So I'm going to factor out an e to the negative x because that's the lowest power. And we'll be left with 2e to the 3x. Be careful with your exponent rules there. Minus 1. Still not very intuitive, but we've got one thing times a bracket equals 0. So one of those things has to be 0. But one thing we know about the exponential function is it can never be 0. So we don't have to worry about this function right now. We then need 2e to the 3x minus 1 to equal 0. If we solve for e to the 3x, just by doing algebra, we get e to the 3x equals a half. How do we solve for x? We ln both sides to bring the exponent down. So ln, and we get 3x times ln e, which is 1, so that goes away, equals ln of a half. X equals ln of a half divided by 3. So pretty intense to even get the x value. Remember, that's where the derivative equals 0. We're going to toss that on a number line. So this is the spot ln of a half over 3. And then we want to plug in numbers larger than that and numbers smaller than that into our first derivative to see if we'll get a negative value or a positive value. So what happens when we put a really big number in here? Right, this is our first derivative. When we put a really big number in for x, this is going to become positive. When we put a smaller number in for x, like a negative number, the whole thing will become negative. And you can test that out by plugging in different values for x and seeing what the derivative becomes. Therefore, our domain for increasing, the function is increasing wherever the derivative is positive. So that's from ln of a half over 3 forward to infinity. For decreasing, it's negative infinity, because we can put any x value into exponents. It just alters the actual value that comes out. So from negative infinity to that point, ln of a half over 3. So that's part A. Again, increasing, decreasing, that's the first derivative test. Find where it equals 0, put that on a number line, and then test either side of that value back in your derivative to see if you get positive or negative. Let's pause and look at B. Okay, B is right in line with A. Actually, it's not too bad once we've already found the spot where it equals 0. It says find the maximum and minimum values. Maximum and minimums always happen when the derivative is 0. So we found that the derivative is 0 when x equals ln of a half over 3. But when it asks for the values, max and min values, that means they want the y value. So we have to actually plug that back in. So we want to find f of ln of a half over 3. If we plug that in everywhere we see an x, we get 2 times ln of a half over 3 plus e to the negative ln of a half over 3. What does this equal? So we've got e to the 2/3 ln of a half. Not the nicest thing, but this will end up being just whatever's inside, so 1/2 to the 2/3. That's the rule when you have an exponential to a ln. You could also do this in your calculator. And same thing here. We'll get plus 1/2 to the negative 1/3, because that's the coefficient out front. So this should be our y value. Now the question is it a maximum or a minimum? Well, we go back to our first derivative test. We said that it's negative to the left, so that means our function's decreasing. Positive to the right, that means our function's increasing. So down to up, that must be a minimum. So this is the local minimum value. Let's do part C. Okay, for part C, it asks for the intervals of concavity and the inflection points. So that should be our trigger. Those should be trigger words for the second derivative. I've written our first derivative here that we already did. The second derivative will be 4e to the 2x because we rewrite the e part times the derivative, so 2 times 2 is 4. This will become plus e to the negative x. So that's the second derivative. We need to find the intervals of concavity and the inflection point, so it's the exact same thing as what we did with the first derivative, only we do it to the second derivative. So I'm going to simplify this again because we're going to want to set it to 0. So I'm going to factor that e to the negative x out. We get 4e to the 3x plus 1, and I'm going to set this equal to 0 because we can find the inflection points quite easily. Once again, we don't need to worry about e to the negative x because that can't be 0. So we want this bracket to be 0. So that's going to be e to the 3x equals negative 1 over 4, just by algebra. So I'm going to say x equals ln of negative 1 over 4. So I'm going to essentially ln both sides, divided by 3. Now, what's the problem here? Oh, we cannot take the logarithm of a negative number. In fact, if we look back to the bracket here, we need this to equal 0, but there's a plus 1 there. This can never be negative, the 4e to the 3x, right? Exponentials can never be negative, so there is no inflection point. We just now need to figure out what the concavity is. So is it concave up or concave down? Well, this is our second derivative. Both the exponential functions are always positive, so we know our second derivative is always positive. A positive second derivative means it's concave up from negative infinity to infinity. So this is a lot easier actually because there was no value that made it 0 and we didn't have to test either side. We just had to realize that the exponential functions are always positive no matter what x is. Hopefully this is helpful. You can see the ties between what you do for the first derivative to find maxes and mins and what you do to the second derivative to find inflection points. You can always email us more questions at info@arnoldtutoring.com. Thanks.